Thanks for coming out, everybody. My name is Ben Wicks, and I'm an Android developer at Buildertrend. Recently, I've been investigating how we can cut down the amount of time it takes to do our largest data request from the web and process it. So tonight, I'll summarize what I've been learning recently about that, and I'll show you guys how you can improve your user's experience by cutting down the time it takes to transfer data and make your app faster at parsing data. So tonight, I have 4 points to go over. Actually, go back quick. I have my sample code at this URL. It's also on the data page if you guys want to follow along. And I'll get to it eventually and show you on the screen too. So in these 4 steps, I'll show you a comparison of several different ways to decode and encode data with Android, and hopefully it can help you guys decide a way that will work and suit your app's needs. So to get on the same page, decoding and encoding, what I mean by that, decoding and encoding structured data, I'm referring to taking the textual representation of your data and deserializing it into an in-memory Java object to use in your app, and then serializing it back into a textual representation of the data. So this is important because it's a way for your app to interact with the outside world and data that lives somewhere else. So a stat that I read while I was researching about this was from Google. They say that you can decrease the amount of data that you send by 3 to 10 times, and you can increase parsing speeds by 20 to 100 times simply by changing the data format that your app uses to transfer data. So that's pretty crazy numbers, and hopefully I can show you tonight how that's possible. So one important thing to note from the graphic here is my text file is representing an XML document, and XML is a human-readable format. Each byte and the corresponding byte array there represents an ASCII character, and this format makes it possible for the data to be both human-readable and machine-readable. But note also that it's possible for your data to be encoded in a binary format that's not human-readable. And that's what Google's talking about in their quote. So in a few slides, we'll take a look at their format. So next, these are the 3 formats that I chose to go over that are the most popular ways to transfer data in apps today. First, I'll talk about XML. Who here is familiar with XML? Cool, just about everybody. And who has used XML to interact with data in their Android apps before? Cool, half of people. Does anybody know what XML stands for?
Extensible markup language.
Extensible markup language. Awesome. Does anybody know when XML was first developed?
1924.
Yep. 96 is what I found 20 years ago. And I say one of the pros about XML is that it's self-describing. Does anybody know what I mean by a self-describing data format? And I say somewhat there. I'll explain that. So XML is self-describing. That means that each of the tags, the string that is inside of the tag there, gives you an indication of the type of data that's in that field. It also gives you an indication of the meaning of that data. But it's only somewhat self-describing. The machine that's parsing XML can't make any sense out of those keys unless you tell it what they do.
How do you know what type it is? It's based on regular expression.
So you can kind of tell what type of data is going to be in the tags based on the name of the key, so you can guess that it might be a date if it has date in the name. Or that's what I mean by that. I don't know if XML has a way to tell you what data type is sorted. Go ahead.
It's XSD, right? Yeah, XML combined with XSD. You can embed the tag within the element itself. So, as an integer, you can put in the element name itself. Say, hey, this is integer.
Yep. So XML has a way to describe what type of data will be in the tag. Yep. Yeah. So this is it's really hard to see up there probably, but it's the first record from my sample data set tonight. My sample data set is just a list of species that I found on gbif.org, free database about genetic biodiversity. So an important thing to note about XML is that there are all these special characters, the less than, greater than signs, and the new lines in the tabs, if it's formatted pretty like that, that just take up extra space. And so each field on each object in your data has two tags associated with it that are essentially extra data that you don't need. So that's XML. Next is JSON. Who has used JSON in their apps? Cool, pretty much everybody. Cool, who knows what it stands for? JavaScript notation. Yep, JavaScript object notation. Yep. Who knows when it was first developed? It was developed in the early 2000s, so that's what I saw. 2001 is the first time that that acronym was associated with it. That's 15 years ago this year. And again, it's somewhat self-describing. There's a tag, the key for each value, and it tells you something about what the value is going to be. And JSON can also maybe tell you a little bit about the format of the data. It's going to be a string or an integer. Tell you a little bit about that. But again, it's only self-describing to people. Machines can't tell anything about the data unless you help the machine. So this is the same one record from my sample data set. Note how each key is spelled out, and for each record, each entry, the same key is spelled out for each field in that object, so it's extra data delimiting your fields. So next is protocol buffers. Who is familiar with protocol buffers? Protocol? A couple people, maybe. Okay, so hopefully I can show you guys a little bit more about protocol buffers tonight. So protocol buffers can be abbreviated to protobufs, so I'll probably try to refer to them that way tonight. Has anybody used protocol buffers in your Android apps before? Okay. Nobody? So at Builder Trend, we're just starting to investigate how we might be able to use protocol buffers. I was kind of surprised to learn when they were first released. They were first released in July 2008, so that's already 8 years ago this year. And they have been developed internally at Google and used internally at Google before 2008, but now they're open sourced and available for anybody to use since 2008. So you can see in the screenshot, the first three records from my data set are shown there. I guess it's really small, but you notice that some of the text is readable, encoded with ASCII, but the delimiters are binary. They're not human readable. They're not self-describing. The tags don't give you any indication of the type of data that's in there unless you tell the machine how to understand it.
What do the bold characters mean? Are they like?
They're just binary that don't convert to any ASCII character. So I'll get into exactly what those are in a couple more slides. But basically they're delimiters that give an identifier to each field in your objects. So not self-describing, but more compact. That's the benefit of protocol buffers. Another big benefit is that they're forward and backward compatible, so you can change your definition for your data. You can add fields or remove optional fields and not have to worry about existing apps breaking because of that. Also, Google has made tools available for a bunch of different languages to use protocol buffers. So that's a big benefit, is that you can write your definition for how your data is structured once, and then you can reuse it on your client side and your server side implementations. And I'll get into how to write a message in a couple slides. But like I mentioned, some of the downsides of protocol buffers is that they're binary format, so they're not human readable, they're not easily debuggable because of that. So you have to have the message, which is a keyword in protocol buffers. You have to have the message file to decode or understand the protocol buffers files. So in the next slide, I'll talk about how protobuf files are encoded and generated from a message. So this is the message definition that I wrote for the demo app, and I'll pull it up in Android Studio. Easier to see. So the great thing about protobufs is that you write this .proto file once, and then you use it in all of your implementations. So if anybody wants to follow along, now's a good time to get started looking at my sample source. Let's see, does anybody want help finding the GitHub repo? Follow along, or does anybody? Is anybody there?
It's on the meetup page. Your comment.
Okay, cool. So you can open specieslist.proto to find what I'm looking at here. Cool. So the data that I'm transferring consists of a few thousand species records. It's just a list. And I wrote this message definition and called it species list. So I use the message keyword to define your class or your model for your data. And then I use the repeated keyword here to indicate that I'm going to have one or many messages of type species in my species list message. And next I write a nested species message. And this is where I tell the message what makes up the species class. And then for each field in the species message, I use the optional keyword to indicate that each of those fields may or may not be present in the records of the data that we're looking at. And this is what Google recommends when you're writing your message definition, is to declare your fields as optional. You can also declare them as required if they're always going to be there, but should declare them as optional if possible. Because in your data sparsed, if the field's not there, protocol buffers implementations know how to set that field to a default value if it's optional. And each field is given a unique integer ID per message. So in the species message, each field has a unique integer identifier. And if you ever get rid of one of your fields and want to add a new field, you cannot reuse an old key. So, and that key is what the protocol buffers implementation uses to delimit each field. So that's how you can read and decode and encode protobufs with those IDs. I define almost all of my fields here as strings. I have two IDs that are 32-bit integers, species key and parent key. I have two fields that represent dates. Last interpreted is a date in my data, and last chrome is a date. But I chose the string data type because the data that I got my data from had the strings already encoded, or the dates already encoded as strings. Google recommends that you should be using 64-bit integers to store dates and just store them as timestamps, milliseconds since the epoch. I didn't take the time to convert all my dates to that format, but that's what they recommend. Otherwise, it's fine to use a string. So also another side note, looking at this message definition, right here, this field is the class. In this data set, each species has their kingdom and class, order, family, genus, etc. that they belong to. But you cannot use keywords of the language that you're going to implement protocol buffers in, so you can't use the word class as a field. The tools that you use to turn this into Java code don't care, so they'll still generate Java code, but it won't compile if you have Java keywords in there. So that's an important thing to note. In my experiment at work, I had a message called builder to represent builder, and that the tools worked fine to convert that to Java, but the Java generated code didn't compile because those tools also created a static in your class called builder. So just things to note. So you have to be careful about what you call your field names. And also, for the purposes of my presentation tonight, this is a pretty simple message definition, but I linked in the README on GitHub Google's official language guide for protocol buffers. And if you look through that, you can see that it's pretty extensive what types of data you can store. Enums, bytes, booleans, and bigger numbers are all possible. So this is a pretty simple definition. Next, now that we understand some of these common data formats, I'd like to talk about some common libraries for Android that make it easy to decode and encode data with these data formats. So these are the libraries I picked for the demonstration. Are any of these familiar to anybody? Have you used any of these libraries before? Cool. And is anybody familiar with any other libraries that are similar but not on my list for parsing data? Cool. So now's a good time to look through my source code if you'd like. Hopefully you have the link from the meetup page. And is anybody wanting help getting that code on their computer in Android Studio? Okay, otherwise you can just look at it on GitHub if you'd like, and I'll show on the screen too. Okay. So let's look at my data parser's interface. So I wrote an implementation of this interface for each of those 7 libraries. And each one of them can encode a list of species back into an array of bytes, and each one can also decode a file. I just have local files, but you could get it from the web, but you can decode a file back into a list of species in memory. Feel free to look around at my source while I'm talking about it up here. So first I'll talk about the 2 XML parsing libraries, Pull and SAX. I don't know, I didn't look into what that means, but I just remembered today that I was using SAX to parse XML a few years ago on a project. And it was a lot of work, but it was kind of the only option I had at the time. So has anybody worked with either of those 2 on Android, Pull or SAX? A little bit. So the Pull parser is recommended by the Android docs. Both of them require you to write your own implementation. They don't really help you out a whole lot. My implementations took me quite a while. It was really repetitive to write them, but it took me maybe a half an hour a piece to write those. The pull parser has a way to decode XML into your objects, and you can encode it back to XML, but the SAX library, I don't think it had any way to encode data back to XML, as far as I can tell. So anyway, I have implementations of those in the pull parser class and the XML SAX parser classes. Those implementations were 200 lines about for the pull parser and about 100 for the decoding with the SAX parser. So that's XML. Next is the JSON library, the old JSON data. Does anybody use JSON in their apps? So this is my first time working with it for this presentation. Never used it before this, but it was really quick for me. It took probably 10 minutes or so to write what was needed to parse JSON with JSON. Here is probably a good time to pause and help you guys look at the demo application that you can run on your phone if you want to download it. It's in the Play Store. There's a link to it on the GitHub README, or you can just search for structured data demo if you want to get it and play with it and look at parsing data in different formats. Or you can build it from the source. It'll compile. Cool. So my implementation for JSON just had to write a JSON parser class, species wrapper, and I had to annotate a couple of fields in my species class. I can show you guys that quick. Some of you will be familiar with it, but it's the JSON parser. Has these two methods, encode and decode, and this is given to you with the JSON library. This is all you have to do to get JSON into your project. Just add a line for it in your build.gradle file. So this is given to you, JSON builder. I had to tell it how to take strings and turn them into dates by giving it a date format. And then I just had to tell it what type of file that it was dealing with. So that's just a list of species. And also each field in my species class. Actually, only 2 of them had to be annotated with this JSON serialized name. That's a JSON annotation that you tell JSON how to find each field. So for this one, my field name was a little bit different than how I wanted it to be encoded and decoded. Same with class. But other than that, all those other fields, JSON can automatically detect and find based on their variable name. So that's all it took to get JSON implemented for me. Pretty quick. Next, I'll talk about Jackson, which is one that I was more familiar with. Does anybody use Jackson in your projects? Cool, a few people. Cool. So Jackson is also pretty similar to JSON. It uses the @JSON creator and @JSON property annotations to identify your fields and how to create your objects. So I had to write Jackson helper, Jackson parser, and add a couple of annotations to the species class. So I annotated my constructor with @JSON creator annotation, and it tells Jackson where to look to automatically generate objects of your classes, and I annotated each of the parameters with the @JSON property to tell it which strings to look for to hook up to each of those parameters. So that's all I had to do for the species class. Jackson helper was just a little class that I wrote some helper methods to read in lists of a certain type. And Jackson parser was my implementation for this, just one line piece to get data in and out. JSON. So that was pretty quick. And since I've been familiar with it, it just took a few minutes to get all that done. And it's just, I think it was just one line in the build.gradle. There was a few actually. Get all the annotations and everything. Next, I'll talk a little bit about Moshi, which was also a new one to me. Has anybody used Moshi in your work? Okay. So Moshi is developed by Square, or I don't know if it's a personal project or not, but anyway, so this one is actually relatively new compared to the others, just a couple years old. So my implementation was also using an @JSON annotation on a couple fields that were different. The variable name is different than the JSON key. Show you the Moshi parser. So JSON adapter is given to you by Moshi. I had to write species wrapper, which I also used in another implementation for a different library. I had to write the date adapter to tell it how to interpret, how to get a date from a string. And then encode and decode were just one line after that. So the date adapter was pretty quick. Easy to write, using the same date format as before. Yep, so that's all that one took. It seemed like it had a dependency on OKIO, and it was also, when I did some memory profiling, it was the heaviest hitter on memory usage in my tests. It was also a little bit slower than Jackson and JSON for me, but it was really easy to implement. So that's my experience with Moshi. And from what I could tell, Moshi is the name of Jake Wharton's dog or something like that, so must be a personal project. So next, I'll talk about two libraries for protobufs. Wire was the library that I've been investigating, and it was also developed by Square. It was released about 4 years ago, still actively developed, obviously. The generated file that it created for me was 600 lines about. And Square was talking about how when they switched from their old implementation for protobufs to Wire, they decreased their apps method count by about 10,000. And I just found Wire to be pretty easy to use. It was a little bit tricky to get my .proto message definition to line up exactly with the package structure that I wanted my generated species list class to end up with, but that worked out. I had to write the Wire parser and a couple of methods in the species class to interchange between the species list and the species. So I can show you what that took. Has anybody tried Wire or heard of Wire? Okay. I haven't used it, but it seems like Wire also has an Android Studio plugin that makes it really easy to generate Java classes from your .proto message definition. So it seems like they're trying to switch it from whatever repo to now into the main Wire repo. So sometime soon. It seems like they've been actively working on that in the past couple of weeks. So might be something cool to look at in the next month. So I'll show you how to use Wire quickly. So Wire, I guess I have the steps in the README on GitHub, but all it takes is to go out onto Maven and Maven Central and download the latest jar with dependencies for Wire, have it somewhere on your machine, and then you can generate Java classes from your .proto message definition with this command. So that runs pretty quick and generates one Java class, and you also need the wire dependency. Somewhere down here. Need that to get it to compile, and show you that. This guy. So this is the code that the wire jar generates for you. It uses a builder pattern to create your objects.
What's the name of that file?
It's specieslist.java. There's probably a couple of that name, but it's in the wire package. Yep. So the wire does all of this for you. You don't have to do any of this code. In fact, I don't want you to touch it. So with this, I wrote wire parser to go to and from the binary protobuf file. So the encode method, well, actually I'll start with the decode method. Take the input stream and you give it to the adapter class that wire generated, and it knows how to decode the input stream into its model that it generated from your .proto file, and then I convert each of those species in that model to my other species class that's just Hojo, and I add that to a list and I return that list. So that was pretty quick. And this method right here, from wire species, basically knows how to convert dates from strings. And then to encode from your in-memory Java objects back to a byte array, back to formatted data. You also use the adapter that wire generates and encode, and knows how to do that. So that was pretty easy to write. I recommend wire. I guess the next one I'll talk about is Google's option for generating and dealing with protobufs. It's called ProtoC. Also released about 8 years ago to the public. Just today I was learning about how Google recommends to use the Nano option on their tool to generate protobufs. Basically their Java implementation of protobufs isn't really intended for Android because it generates tons and tons of code, tons of getters and setters. And when I was using that way, I had a generated Java file that had 3,700 lines, getters and setters, really huge file. But when I used the Nano option, which I think I linked to the steps on how to do that in the GitHub README, I ended up with just 400 lines, so pretty comparable to what Wire generated. So definitely use the Nano option if you're going to be wanting to use this tool for your Android app. Also, I just learned today too that Google has a tool that's a Gradle plugin that basically it's right here. It looks in a certain directory in your project. Under app, there's source, main, and photo. So in this directory, it looks in here for any .photo file, and it automatically runs ProtoC on it and generates Java from those. So that made it really easy, a lot less setup to get that working. I also have the steps for how to generate Java files without using that Gradle plugin, and it took me a lot longer to get that working. So see the README if you want to learn how to do that. All I had to do for this was run a couple more helper methods on my species class to convert to and from dates, and then also the protobuf parser. I'll show you that. Very similar to the wire parser. They make some changes between the Nano option, and the regular Java, not for Android option. So basically, Nano wants you to give it a byte array instead of an input stream. So I did a little conversion down here. And also, it gives you a byte array back So it had to do a little bit more work to get your data into those formats, but ultimately results in a memory usage reduction. So check out the nano option if you're going to look into Google's Proto-C library. Like I said, the steps for how to do that is all in the README on GitHub, so check that out if you want to. Next is the interactive demo. I just did a screen record of my app that I put out there. If you have it on your phone, you should try it out too. Maybe you have already. But my app just shows the time that it takes to decode and encode my data set using each of those libraries. So it's a way to compare time. I didn't put anything in for memory usage, but I was doing a little profiling on my own for memory usage, and I put those numbers in the data parser class, or in the data parser class, maybe. One of those. So the numbers that I found for profiling are right here for function memory. Each of those libraries used to encode and decode data. So anyway, I'll show the video for my screen recording of the sample app to show you guys how much time it took to decode and encode data with these libraries. And also, a quick note before I get to that, if you've been looking at the source code, I used async tasks to do this decoding and encoding asynchronously to not block the UI thread. And I was wondering if is anybody familiar with async tasks? Okay. Is anybody familiar with RxJava? Okay. So I'm not familiar with RxJava, but I'd be interested to hear a talk on it maybe. So that's an option if anybody's into RxJava or has some experience there. So I'd be interested to hear more about that. Anyway, this is what I have for demo. So first is the SAX parser. Took about 4 seconds on its run to decode the records. Whole parser took about 2 seconds to decode and 2 seconds to encode. Moshi, like I said, it was pretty heavy on memory compared to the other JSON parsers.
Yeah, that was pretty JSON.
Yeah.
Is it about the same, or is it
Oh,
still a lot more?
I can show in a second. I have it commented in one of my files. I think it was a good bit more, I don't remember. So you notice that Protobuff's decoding, at least, is quite a bit faster than all the others so far, with Google's option being the fastest at decoding in just one run. A little bit of a way to look at the fastest. Fastest decode was Protobuff, Google's Protobuff. One that took the longest was the XML SAX parser. Jackson was the fastest to encode data back to textual representation. Moshi was the slowest to encode everything back in that run. And here's the file sizes, which I think I also have commented somewhere. So you can see that the XML file is the biggest by a little bit. And both of these, what I used for my data, JSON and XML, were pretty mixed and printed, so they had tabs and new lines and everything. So that makes them a little bit bigger yet, but Protocol Buffer's file is quite a bit smaller. And compressing those files, Protocol file is still a lot smaller. So that's the demo that I have. You guys can try it, do more runs if you want. For the memory usage, Moshi, just a little bit more data on or a little bit more memory usage on decoding. It seemed like it was a lot more, maybe pretty comparable to JSON. But that's what I had for my profiling. So next, there's a video out there that's from, does anybody know this guy's name?
Yeah,
Colt. Yeah. Yeah. So he puts out a bunch of these Android performance patterns videos, which are really, really fun to watch and really interesting. Controversial sometimes, but he's entertaining and fun to watch. And he has a video, season 4, episode 14, that's out there that he talks about protobufs and how they compare to JSON and XML. So search for that and give that a watch if you guys are interested in learning more about it. So this slide is just showing his comparison of the size of the files, raw and compressed, with flat buffers is very similar to protobufs. There's a link in the README to learn more about flat buffers. In blue there, and then red is protobufs that I was dealing with. So definitely the smallest file size using protobufs with whatever JSON format he was showing there. Seems to be a lot larger. XML's a lot larger too. He also has a graph for comparing the times that it takes to decode and encode with those 4 options. So flat buffers is also something to look into. It's geared towards gaming, is why it was developed. Very similar to protobufs, but it doesn't have an extra step for taking the data in and out of the byte arrays. I didn't look into it yet, but definitely something to look into to dramatically reduce your decode and encode times. So that video is out there. Check it out if you have time. Really appreciate everybody's time, and I'd love to hear some questions if you guys got any or any comments. So otherwise, I'll turn it back over to.
I was just thinking about retrofit. Everybody uses it. It supports pretty much all those you talked about, which is really nice.
Yeah, yeah, to get data from the web.
Right.
Yeah,
That's encouraging.
yeah, that's developed by Square.
Yeah. So there.
So that was all done locally on your device, right?
Yeah.
So did you do any network comparisons too?
No.
So I'm assuming it would be equivalent, right? So like a protobuf would consume fast on network.
Yeah, yeah, because those files are maybe like Google Stats said, whatever it is, 3 to 10 times smaller. I forget. Generally, those files are quite a bit smaller in protobuf format. So you don't see that in the sample app, but if you're transferring data over the network, you would see even more speed increase.
Yeah, it would be huge.
Yeah. And they advertise, Google advertises, whatever that number was, up to 100 times faster decode time. Which I haven't seen that yet, but
So is there any way to see like responses from server and Charles? Is there anything you can do to decode those?
yeah, I forget where I learned about that, but I was searching about that and to look at the request in Charles. There's a way for your web requests to send a header with your protobuf data to tell it where to look for the .proto message definition, and Charles can basically look at another file on that machine and find the message definition and give you a plain text.
But if it's so, if you were, I don't know why you would have this and not have the message, but if you were just trying to look at requests that you didn't have a message for, to see maybe if there's an extra field, there's just no way to do that basically.
Yeah,
You gotta work closely with your service team.
yeah, definitely. So yeah, data's in a binary format. You can get to some of the characters if they're ASCII, but it's going to be hard to tell what they mean. Yep.
Did you look into anything besides Android implementations too, like iOS, like how iOS is acting that wrong?
Yeah, I didn't look into it. Google advertises the languages that they support with their tool. I don't think Objective-C or Swift was on there, but I know there are definitely third-party libraries for that, but I didn't look into them. So there are third-party libraries for a bunch of different languages for web apps.